Thanks for the introduction, and thanks for PyCon Korea organizers for the invitation. Today, I'm going to explain about understanding the particle therapy data analysis, and this program is made with Python that I'm presenting in PyCon Korea. And then I would like to expand this scientific method in general case, including deductive and inductive method. So I have two parts. First part is introducing my research product about the program which is called Frog, but also I'm going to tell you about some part how you can handle the medical data. And then I will move on to the scientific data analysis, that what understanding how the scientific method is well interpreted. So the first part is Python-based recalculation program research. First, I assume that many of the audience are not familiar with the field which is called medical physics. So I would like to introduce you about some domain knowledge of this field. So medical physics is study of the effect of ionizing radiation in the body. So what is the ionizing radiation? The light we have here is kind of the radiation, but we don't worry about the radiation. It's because the light that we're using is not ionizing the air or water that cause the serious effect to the DNA. So for the light, we are calling this non-ionizing radiation, while the medical physics is handling about the ionizing radiation, which is containing gamma rays or X-rays that we are very familiar with the medical device. So here is the short history of the medical physics. In 1895, William Röntgen discovered the X-ray, and Marie Curie and Pierre Curie and Henri Becquerel discovered the radium in 1898. And Marie Curie used the X-ray machine, which is called the Little Curie, to make the imaging of the injured soldiers in World War I. And then Benedict Cassen found out the method of the nuclear medicine in 1951, and Sir Hounsfield developed the CT in 1979. This is the history of the medical imaging. And also, medical physics is handling treating the cancers. So in very early stage, it's 1896. In 1896, Niels Vincent used the ultraviolet to treat some disease. And also, Röntgen, the X-ray, was first used for the treatment in 19th. And the radium therapy was introduced in 19,000 to 1915. And this method has been developed to the brachytherapy, external beam radiation, and unshielded source of radiation therapy that we are using to treat cancers nowadays. So I'm working on the particle therapy, which is part of the external radiation therapy. So what I'm doing is using the phenomena of the particles, which you can see here, and at the normal tissue of the entrance, the radiation exposure is lower than the conventional radiation therapy. That's why it's very accurate and has less side effect. The problem is this method is very risky and sensitive. As you can see, the photons that you see here doesn't change a lot of energy, even though there is some range uncertainties, while carbon ions, if you miss it, it's totally a different treatment. So we need to handle this problem, but there are many methods that we can handle this problem, but still not very clear. One of the ways to handle this problem is a Frog platform that I have developed. Frog is a forward calculation program which is calculating the radiation before doing the treatment at CNAO, which is located in Italy, and here located in Germany. And we are trying to aim to match for the very close to the Monte Carlo simulation. However, Monte Carlo simulation is very slow, that we also want the conventional speed. For this reason, we made a program with the GPU-based system. So we have some process of data in the CPU part, and then send all the information to the GPU and do a lot of calculation based on the GPU, and we finally produce the medical output. And this work is all done with Python. So we have the validation here. The agreement of this program must be lying in 5%, which is agreed in clinical protocol. And our program is matching within 1%, while the other commercial programs are matching in 2% or low, or a little bit higher. Also for carbon ions, we have a very good agreement, which means 90% is the very good agreement, and we achieved over 95%. So I would like to introduce you about how I used Python. Here are the modules that I used. One is the pydicom. This is the key of the medical analysis. Pydicom is a module that enables you to read the DICOM format, which is very widely used in medical field. For example, if you want to read about the CT images or X-ray images that we saw in the morning, all the formats are existing in DICOM format. And this pydicom enables you to read all X-rays, MRI, CT, PET, and other images. So this module is one of the key modules to read the information. And for the GPU, I used PyCUDA. So I know that many people are interested in TensorFlow, PyTorch, or other statistical model-based GPU calculation. However, what we're doing is not the inductive method. We're doing the deductive method that we don't use the statistical module, so we directly code everything using PyCUDA. There are other very famous libraries such as numpy, Matplotlib, PyQt, and other modules are used for auxiliaries. So here is the DICOM. DICOM is digital imaging and communication in medicine format. So this is kind of a standard information format to save all the necessary information for the medical purpose. And PyDICOM is enabling you to read those information. Here is the example that if you read some DICOM files with the PyDICOM, you can see those information. So I import DICOM here, PyDICOM, and then I read the file. This is kind of a dot file that existing only one slide with the 3D matrix. So this is only the part of the DICOM format. However, we can understand how it is constructed. So when we load those memory, then we have like a specific character set is kind of our information. Also, we have patient name here, which is anonymous already, operator's name, that the clinician's name exists here, and also we have the study instance, which tell you the date and other information together. So if you want to treat any medical information, you need to understand how the PyDICOM works. So here is the data that I used in the PyDICOM. For preparing the treatment in the particular therapy, there are 4 types of DICOM files we need. One is the CT file set, which is very well known for the public. The second one is the RT dose that we previously saw, which contains the information of the radiation dose in the patient body. The third one is the RT struct, which contains the information of the human organs in the contouring format. And the last one is the RT plan, that how we are going to radiate patient, and this is one of the most important data for the calculation. So here is the example of the CT file. This is how I read with PyQt for one single patient. And we have the CT image slice, which contains all the information of the array, 2-dimensional array. Also, it contains the image size. It contains the size of the pixel in millimeters. Also, the origin point, which is called the image position patient. This is the image position patient, and this is the origin of your CT. Also, pixel spacing is defining the distance between two pixels, and patient position is showing you if it is prone or supine position, and the location of the image and so on. Those informations are contained in CT and frog process it. Here is the Dodge file. It also contains the image size, image position patient, which is the origin of the Dodge map, and the information of the three-dimensional Dodge matrix. One important thing for the clinicians are the RT struct. This file contains almost all the information about the organs. So here is the example. The red line, of course, the color is arbitrary for every case, but however, in this image, you can see the red colors here. This volume is the cancer area. The clinicians are already defined. And here is another organ that we need to avoid for the treatment. So those informations are provided for the to the medical physicist to calculate and prepare the plan. And the RT plan contains all the information about your treatment plans. So when you have the beam, the radiation should be very accurately delivered. So the position where you are going to deliver the radiation is strictly defined here. There are two informations. One is the scan spot position, which is the distance, X and Y deposition from the origin. And the second one is the weight, which means it is the numbers of the total particles will be delivered to the target. So those informations are the raw data that we need to reprocess it. So what I'm doing is recalculating those informations using the different physical model with another system to understand how the physical interpretation of those informations can be varied due to the models. So this is fully a scientific-driven program, but also can support clinicians. And here are many people, or most of the people here are developers, so I would like to go for a small example here. So many people might use the PyTorch or TensorFlow, but I don't think many people use the PyCUDA. So the reason that I'm using PyCUDA is already I said, I'm not using the statistical model, I'm using the physical model. So I need to use PyCUDA and making all the modules that I need. So what I am doing here is loading PyCUDA and PyCUDA initialization and source module. Source module is working to transfer the C code or the CUDA code to the Python format. So these three modules are important. Luckily, PyCUDA also supports numpy module, so we can use numpy array to use PyCUDA. So if we define 4x4 size random matrix, then we have an example here. So we can see 4x4 information, which is to the float 32 format. It's because if you use double, the calculation time for the GPU is getting twice longer. So we are changing all the format to the 32-bit, and then we allocate it to the GPU. So what we have now is all the information in the GPU memory, and we only have GPU memory address here. And then here is what we are doing. We have the core part, which is multiply 2 from the origin matrix. So here we define global void float A, which will have one matrix input here. And here the IDX is defined as the thread IDX-X, which is corresponding to the 4 arrays here. And thread IDX-Y is corresponding to the second matrix that we are defining 16 CUDA cores that's going to work here. And finally, we run the code, and after we see the result, we can see that here the matrix is doubled automatically. And Later, I will explain you about the performance of this PyCUDA. However, when you process the DICOM, this is kind of a very important research in the performance and accuracy. When you are doing the science, the performance is not only the issue, but the accuracy is also the issue. So the commercial treatment planning system used a double Gaussian distribution model and FLUCA simulation, which is confirmed as CERN and also used in Hadrontherapy in European countries, used the Monte Carlo-based calculation. However, Frog is using triple Gaussian distribution that postulates much better than the commercial one, but almost as fast as the commercial treatment planning system. So as a result, we find out that different model postulation also drives the different result. Monte Carlo simulation is very accurate, but it takes a long time. When you need to calculate one patient, we approximately need 72 hours with the 40-core cluster. However, Frog can calculate almost 300 times faster, and average calculation time is 90 seconds. So the performance of the calculation is very fast, but the agreement between the Monte Carlo simulation and Frog is only 1%. So this means that Frog is well postulating the result of the Monte Carlo simulation with the very high performance. So I get funded from Medicis ProMed, which is a Horizon 2020 research project, and this is kind of my contract that I need to mention this project for every time for my presentation. So the chapter 1 conclusion, particle therapy is one of the very accurate radiotherapy methods with the low side effect. However, we have a lot of uncertainty issues that we need to solve, and I worked on that part and we achieved a very good result using Python, and this will be published tomorrow. I'm sorry, this will be submitted tomorrow. Now, I will move on to the second part, which is the scientific data analysis. So what I did, the way that I used the GPU is a scientific way, which is different from the machine learning or AI or some deep learning, which is a very hot topic nowadays. So I would like to introduce you for some approach method if you are interested in those fields. So first, if you want to talk about science, you need to understand what the modeling is. The definition of the scientific modeling is the aim of which make a particular part of the figure of the world earlier to understand, define, quantify, visualize, or simulate by referencing it to existing and usually commonly accepted knowledge. So I would say science, 80% of science is just modeling, not the data. So you can see one very famous model, which is called the standard model. Here is the Lagrangian here, and this is all the deductive term of Lagrangian here. So those models are postulating a very small physical world. However, here is the climate change model, which is varying a lot. In early stage, we only had the CO2 emission. However, a little bit later, we have cloud, we have some other ocean effect, and also the activity of the humans and some other materials, and we are making it more accurately. So if you want to understand data, you need to understand the model first. So here is how we understand the data. This is the free-form model. It is very simple. The distance of the fur is 1/2 gravitational acceleration constants multiplied by time square. This is middle school level physics. However, when you have the data, you just feed it to the model. You measure the time and you just put the distance of the movement. And then you have a very good plot. So then, did we find out the law of the universe? Can we use it for every case? Obviously not. So we are going further way. The most important and traditional scientific method is deductive method. As we see, the classical mechanics is one of the very well-known scientific model. However, we also have the fluid mechanics or standard model and etc., which is mathematically reasoned for every term. The another way is the inductive method. Inductive method is reasoning by observed data. So you can see the support vector machine or neural network and some Gaussian process, linear regression, multivariate regressions are all in inductive method. So, does the deductive method means that deductive method is physics and statistical method is inductive? No, it's not. So we are going back to the past to understand how the physics are using the inductive method. Johannes Kepler is very famous for Kepler's law, which drive the law of gravity for Newton. However, his work was driven from Tycho Brahe, which was the teacher of Johannes Kepler, and he measured all the movement of the stars with the naked eyes in 45 seconds. So with his very accurate observation, he made a lot of Johannes Kepler could fit empirically the trajectory of the stars, and he found out that it's not a circular way, but it's the eclipse way. So in science, inductive and deductive methods are well known and widely used from the long time ago. So why I'm talking about deductive method and inductive method? Deductive method and inductive method are very different from the extrapolation. So here is the example. The blue line here is the classical mechanics, the energy-velocity relation. However, the green line is the special relativity relation. You can see that in the very low speed, the difference of them are very low. However, when the speed is increasing, the difference is increasing. So at certain point, we cannot extrapolate the Newton mechanics, but we need to go on to the special relativities. But in certain boundary condition that based on your problem set, you can extrapolate the deductive method. However, you cannot extrapolate the inductive method. This is one of the examples that we can saw in the PyCon Korea last year. So they fit one-dimensional linear regression to the second-order polynomial data set, which is not a good way, but however, this is the linear regression. And they gave you the boundary from 0 to, I think it's 15 here. No, it's 10, sorry. So in this boundary, this regression model is working. However, if you go back a little bit far away from the domain, you cannot postulate anything, and the postulation is going more bad and bad. So this is why, when you're using the inductive method, you need to be very careful. So this is the limitation. If you use the law of physics, at certain singularity point, you cannot do the extrapolation, but until the singularity point, you can extrapolate it. And it is very easy to find out that you can do or cannot do the extrapolation, because you can certify your model based on the data. However, if you make a model empirically, you cannot prove your model empirically. That is the difference. So here is the difference between the deductive method and inductive method. For model validation, which I already said it's more than 80% in science, when you do a validation, you can use empirical data to prove your model or validate your model. However, if you want to prove your inductive method or inductive model, then you need to provide a lot of other parameters that your model is working. The first one is the domain. You need to clearly provide the domain that the model is working. Of course, it is not enough. You need to provide more statistical validation parameters. And also, you need to provide the threshold that why that validation is working. So for accuracy, when you do a deductive method, it is highly accurate. But inductive method is always the approximation. Also, if you want to know, if you need the domain knowledge, the deductive model, you need to know clearly about the field. But inductive model, you don't have to. But at least you need to know the domain knowledge as much as you can to prove your method. So if you do a it's extrapolation. Extrapolation, it's obvious. You can do extrapolation with the deductive method, but you cannot do it with the inductive method. So this is why you need to learn science to do a machine learning or some deep learning. However, if you don't know about it, then you will do some mistake. I will give you some example about that case. Last year, I saw some presentation that saying machine learning is sacrificing the reasoning to have higher accuracy. This is totally opposite. Machine learning is sacrificing the reasoning and sacrificing the accuracy to work easier. That's the point. It's not accurate. So if you understand if it was an inductive method, then you wouldn't say that this is not an accurate postulation. Also, some people say that data is getting very important nowadays. However, in 287 before Christ, which is 2,300 years ago, Archimedes of Syracuse find out that the crown contains both silver and gold. How did he do that? He numerically proved that the flooded water is different from the gold. So they numerically defined the data of the mass and the density relation. So data was very important from the very past. It's not the recent era that we are using data. However, let's go back a little bit more. When even humans didn't have any civilization, the poisonous mushroom, which is very colorful and bright, is a classification method. So humans were already using the inductive method even we didn't have any civilization. So data was always there. Humans were always using it. It's not a recent advance. And this is a little bit dangerous. There was another presentation that talking about the data pre-processing, and they're saying that they put some data mean value to the empty set. This is called data cooking. The Professor Huang did it before, and this is a huge ethics violation that will screw up your career. If you do it once, your career is over in scientific field. But if someone doesn't understand that this is important, it is the importance of the scientific method, they might say this. So if you really want to be careful and doing a real job, scientific knowledge is very important. Also, another case that you need to know the science, including statistics, is the second example, overfitting. Not only this case, but a lot of blogs are saying that overfitting caused from a lot of training. But overfitting is nothing to do with the training. Overfitting is just having more parameters that then can explain the data set. So also we have the underfitting. If we have less parameters, then we can explain the data set. It's called underfitting. That we saw this before. This is the case of the underfitting. So, and I'm really sorry, but this level is the first day of this statistical class in the bachelor freshman level. So what I'm criticizing is not the hard one. What I'm criticizing is very easy one that people never cares about. So if you want to do a real job, please take care about the real knowledge that many people are already worked on. So as a conclusion, AI, machine learning, and deep learning is not a brand new magic. It's just a scientific method that scientists were using from the long time ago. And also understanding of data and postulating phenomena is very traditional work. So when you're doing some postulation, that was science. That was how the philosophy of ancient Greek. So please, let's get back to the basic and let's try to understand the good ideas that bright people already have done. Thank you for listening.